Greetings, my dearly beloved students. Um, Welcome to question 5 of the tutorial sheet A2. The magnitude and we are determining in each of the following the magnitude and direction angles of the resultant force. Then determine the magnitude of the rectangular components of F1 along the line of action of F2, and then the angle between F1 and F2. Alright, so let us just begin to solve for Roman numeral 1. Okay, so no, okay. So the first thing we have to do is to convert F1, F2 and F3, as we can see them in the diagram, into Cartesian vector form. So we'll need the position vectors and get the unit vectors for each of those respective points. That is position vector to A, position vector to B, and position vector to C. So we are just going to do just that. So we'll start with A. Remember, our aim is to get the unit vector in the direction of A and multiply by the magnitude of F1. So we'll get the position vector A. So RA is equal to, when we say RA, we mean position vector A. So according to the coordinates of A, RA will be 2.4 I plus 2.7 J plus 3.6 K. Okay, and to get the unit vector, we divide by the magnitude of RA. This will be equal to the unit vector in the direction of A. So this will be over the magnitude of RA, which is the root of 2.4 squared plus 2.7 squared plus 3.6 squared. And this unit vector gives us yes, just trying to calculate here. Okay, so it gives us 0.4706 I plus 0.5294 J plus 0.7059 K. Awesome. So that's the unit vector in the direction of A. So then our F1 as a vector will be equal to F1 multiplied by UA, which will be equal to 272 multiplied by the UA, which is this one here. And when you do that multiplication, you should definitely get 128.00 I plus 144 J plus 192 0.00 K. All these it's newtons. All right. So we've done that for F1. We need to do the same for F2. So unit vector in the direction of B will be equal to let's see the x component. We have 0.6 I and then that's minus 1.8 J, and then in the K direction it's plus 2.7 K over the magnitude of this 0.6 squared plus 1 minus 1.8 squared plus 2.7 squared, and this unit vector will be equal to 0.1818 I minus 0.5455 J and plus 0.8182 K. All right. That being the case, then our F2 as a vector is equal to the F2 magnitude multiplied by the unit vector B, which is equal to the F2 we've been given to be 500 multiplied. This is not cross, it's just multiplying. It's not a cross product, it's just a multiplication sign. So we're multiplying by unit vector in the direction of B, which is this. And when you do that, your vector for F2 will be equal to 90.90 I plus not plus, sorry, minus, has to be minus 272.75 J, and then plus 409.10 K. All these it's newtons. Okay, we'll do the same for F3. So we are saying F3 as a vector is equal to, the magnitude of F3 is 650 multiplied by the unit vector, which is in this case it is 3.6 I. That's the position vector minus 2.12. No, I think I am getting it wrong here. Okay, it should be 1.2. As you can see, that 1.2 here. Let's see what we can put here. Comment. to insert comment, drawing, pencil. Yeah, right. So the 1.2 is there. Okay, coming here, we are having plus a small 0.9 k. This is 1.2j. Then over this magnitude, which will give us which will be 3.6 squared plus minus 1.2 squared plus 0.9 squared, and this will be equal to 600 I minus 200 J plus 150 K. So all these, it's in newtons. So that's the third force. I hope my graphic calculation is making a bit of sense. So let's see if we can scroll up with this thing. How do you do it? You click. No. How do you move now? Okay. You need to be done inking, and then that's when you move. Okay, fine. Alright. So we get back to inking. We change. Alright. So then now we're told to find the magnitude and direction angles of the resultant. So our resultant then, which is FR, will just be equal to the summation of F1 as a vector plus F2 as a vector plus F3 as a vector. Okay, so when we do that, that is, you sum the I components alone. Okay, so come on, there should be another way of moving. Right clicking is not working. Okay, I guess you just have to go to be done. Okay. Sorry, just getting familiarizing myself with this too. Just trying to get familiar. Oh, okay. So with the direction again. Okay, let's continue. So then with this, I'll add the I's are on, so the 128 and the 90.9 and the 600 there. If I add those, they'll give me 818.90I, and then if I add the 144 and then minus the 272 minus the 200, I should get 328.75 J, and if I add the Z component, I get 751.1 K. So this is our resultant force. Finding the magnitude of this resultant, we'll have FR, this will be equal to the square root of 818.90 squared plus minus 328.75 squared plus 751.1 squared, and this is coming to 1158.80, yes, newtons. So you have found your magnitude. Now let's find the direction angles. Okay, so definitely this question is loaded. The direction angles, let's find the direction angles now. Okay, so for we have the magnitude here, we have the components there, so it's not a problem. We know that our alpha, which is the direction angle with respect to the x-axis, is equal to the arc cos of, this will be 818.9 over 1158.8, and this will give us 45.03 degrees. The beta is equal to cos inverse of minus 328.75 over 1158.8, and this will give us 106.5 degrees, and the gamma is equal to the cos inverse of 751.1 over 1158.8, and this will give us 49.6 degrees. Okay, so we have found the direction angles. I want to say for part A, these are the answers. So answer. So this is for part A. For part B, we are told that we need to find the component, the rectangular component of F1 in the direction of F2. Now this is very, 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 extremely very simple. Why? Because we have already okay, let's see if we can move this now. Okay, so we are moving the board this side, sorry, I'm still getting acquainted to this, but should not give us any problem. Okay. So moving forward, here we'll need a unit vector in the direction of A, isn't it? Yes. We need a unit vector in the direction of B because that's where F2 is. That's the direction of F2. And then we'll dot product it with the with the F1. Okay, so it's not actually, we already have those we calculated, so we see that we that's the question B, what it is asking us to do. If you just if you take time to see here, you'll be able to know. Determine the magnitude of the rectangular component of F1 along the line of action of F2. So we just need the direction of F2, which is a unit vector in that direction, and then F1. So let's just do that. We already have the F1. Okay, so we already have F1. Okay, F1 as a vector, it is equal to 128 I plus 144 J plus 192 K. Awesome. Now the unit vector in the direction of B, we calculated it to be I'm remembering. Okay, yes, so it was 0.1818 I minus 0.5455 J plus 0.8182 K. So we have these two. So then the F1, no, it's not a vector. Sorry about that. So what we see here is that the F1, oh no, not again, F1 in the direction of B, okay, will be equal to F1 dot UB, okay, and we know the dot product, it's simply multiply the I, multiply the J's, multiply the K's. Okay, so it will be 128 times 0.1818, and then plus you have 144 times negative 0.5455, and then plus 192 multiplied by 0.8182. Awesome. This will give you a scalar, not a vector, it's a scalar, and the answer here will be yes, what will be the answer here? Let's just do that. Let's just do the calculations. We need to verify. You need to verify this in case I've made a mistake. 128 times 0.1818 plus 144 times negative 455 plus yeah, plus 192 times 0.8182. Sorry, so I'm doing the calculation on this side, and my answer seems to be just what it is. So I'll just go ahead and put that answer, which is 101.8 0.81 newtons. So that is indeed what is regarded as the direction of the component of F1 in the direction of F2. So we found that. Now I want to find the angle between F1 and F2. So we know again that to find the angle, it's simply using the same dot product and then finding the what? The inverse. If you are using the unit vectors, you'll find the cosine inverse of the dot product of those two unit vectors. But if you are using the position vectors or the forces themselves, then it will be something like that angle, which we'll call the angle between they will call it phi, is equal to, you have it's the cos inverse of the dot product of F1 dot F2 over the magnitudes of F1 multiplied by the magnitude of F2. So that will give you the answer. But the magnitude of the unit vectors is 1. So I'll go with that. So phi is equal to cos inverse of the dot product of u b dot u a, meaning unit vector in the direction of b and unit vector in the direction of a. Okay, so this is equal to the cos inverse of you are going to press in now, let's this be square brackets, then you have 0.4 no, okay, that was UA, but I've already started with UB, so let me go with UB. So this is 0. F1 and F2, isn't it? 0.1818 times 0.4, that's the unit vector for F1, it's 0.44706, and then plus again we'll have for B as negative 0.5455 multiplied by the one for A, which is 0.5294 there, like that, and then again plus you have 8182 multiplied by 0.7 059. Okay, so uh, having sure that you have having made sure that you have done everything accordingly. Oh, come on, come on, we are trying to scroll up. Do we? Okay, just okay. Still trying to get getting used to on this thing, but we are together. So this will be just 0. So this will be cos inverse of 0.37433. Let's get it there. And the answer will be phi is equal to 68.02 degrees. Alright, so that is our final answer. So this is the answer for part C, and for part B we really need to learn how to scroll on this thing, otherwise part B, it's the one we found up there, the answer we found up there, which is yes, this one, which is, this is answer for B, for part B, and it's answer for C. This is answer for A. Okay, thank you.